That's the natural expectation of the subject matter. Metal is born strong, it withstands air, water, salt, time, and slowly returns to the reddish dust of oxidation. Rust is not an accident. It is the inevitable fate of iron exposed to the world. And yet, scattered throughout Scandinavia, archaeologists continue to find objects that contradict this silent rule of nature. Nails buried for almost 1,000 years. Chains retrieved from the bottom of old ports. Tools forgotten in damp soil, where any modern metal would have disappeared in a few decades. They shouldn't be intact. But they are. For a long time, it was believed that the Vikings simply possessed inferior iron. Crude, primitive, produced before modern technological advancements. A warrior's society, practical, far removed from what we now call materials engineering. The popular image is well known. Blacksmiths enveloped in smoke, heavy hammers, intense fire, artisanal production limited by a lack of scientific knowledge. A comforting narrative, and profoundly mistaken. Because what archaeology has begun to reveal in recent decades points not to technological ignorance, but to something far more unsettling. The Vikings may have understood iron in a way that modern industry has failed to do, not as a product, but as a living process. In the cold regions of Northern Europe, iron wasn't simply extracted from the earth, it was literally cultivated. In Scandinavian swamps, microscopic bacteria slowly transformed minerals dissolved in the water into deposits rich in iron oxide. Over years, these invisible organisms created natural metallic layers, the so-called swamp iron. The ore did not come from large, deep mines. He was growing. Men walked through the swamps, observing the colors in the water, the textures in the mud, the orange reflections beneath the dark surface. Knowing where to collect the ore required experience passed down through generations. It was less about mining and more about reading the landscape. The first secret was already there. Viking iron was born different. Loaded with organic impurities, natural silica, and small amounts of phosphorus, it seemed imperfect to the eyes of modern metallurgy. Today, the industry seeks absolute purity, rigorous chemical control, predictable composition, structural uniformity. The Vikings did the opposite. They were working illegally, and this irregularity changed everything. When the ore was taken to the primitive furnaces, no temperature was perfectly controlled. The heat varied. Oxygen entered unevenly. The charcoal burned, creating unstable chemical atmospheres. To a modern engineer, that would be considered a mistake. For the Nordic blacksmith, it was the beginning of the transformation. The iron did not melt completely as it does in modern industrial blast furnaces. Instead, it formed a spongy, incandescent mass called bloom, a living cluster of intertwined metal and slag. A uniform metal did not form there. An organic structure emerged. Each hammer blow served not only to shape the piece, it served to reorganize the interior of the material, expelling some of the impurities while preserving others. Microscopic layers began to align, creating an invisible pattern that no blacksmith could see, but that they learned to feel. The sound of the hammer indicated density. The color of the glow revealed the internal temperature. The impact resistance indicated when to stop. Knowledge was not written down. It was incorporated into human gesture. And slowly, without chemical formulas or microscopes, they were building something unexpected, an iron that did not fight against nature, but cooperated with it. While modern metallurgy seeks to eliminate imperfections, Viking iron preserved microlayers of vitreous slag distributed throughout the material. Centuries later, microscopic analyses would show that these inclusions acted as natural barriers against the spread of corrosion. Rust was starting, but it wasn't spreading. The material itself interrupted the process. What appeared to be a defect was actually protection. And then the inevitable question arises. If modern science possesses more technology, more control, and more precision, why do so many contemporary metals age faster than those forged in small workshops illuminated only by fire and experience? Perhaps because Viking iron was not solely the result of ancient techniques. Perhaps it was the result of a forgotten philosophy, a form of engineering that didn't try to dominate matter, but to learn its limits. During the long nights in the north, inside wooden houses warmed by constant fires, the blacksmith did not produce disposable objects. He created tools destined to last for generations. Each piece carried accumulated time, not only in its future use, but already incorporated during its creation. Metal was treated as something that would age along with the people. And this intention changed the very way of manufacturing. Because the real mystery may not lie solely in the iron, but in the human relationship with that which builds. And as we delve into the past, a silent suspicion begins to emerge. Technological advancement may have made us more efficient, but not necessarily more durable. For centuries, rust was believed to be merely a simple chemical reaction. Iron, oxygen, and moisture initiating an inevitable process of decay. Modern science describes this phenomenon with mathematical precision. Formulas explain oxidation. Laboratories reproduce the process in a matter of hours. But what the Viking remains reveal is something more complex. Corrosion is not just chemical, it is structural. When researchers began analyzing electron microscopes applied to Scandinavian artifacts, they expected to find a slowly degraded material preserved by environmental chance. What they found was the opposite, an extremely unusual internal architecture. Viking iron was not homogeneous. He was stratified, like wood growing in annual rings, like ice forming successive layers throughout the winter, like a living organism that adapts to environmental pressures. Modern steel production follows a fundamental principle: eliminate variations. The industrial goal is to create perfectly uniform, predictable, and replicable alloys on a global scale. Each steel bar must be identical to the previous one. Each chemical composition must adhere to rigid standards. Absolute efficiency. But uniformity also creates vulnerability. When modern steel begins to oxidize, corrosion finds a continuous path. The internal structure offers little resistance to the advance of rust. Once started, the process spreads relatively freely, weakening the material from the inside out. The iron forged by the Vikings worked in a different way. During the repeated hammering process, small amounts of slag, glassy residues rich in silicate, remained trapped inside the metal. At first glance, this seemed like a technical imperfection. However, these inclusions created internal microboundaries. Each layer acted as a microscopic obstacle. The rust was spreading. I encountered resistance, and it slowed down. It was like trying to cross a dense forest instead of an open field. The corrosion didn't disappear. It was being controlled. Unbeknownst to them, Viking blacksmiths were producing a material with behavior similar to certain modern high-engineered steels. Alloys designed to fail slowly, never suddenly. But the story becomes even more intriguing when we look at the type of fuel used. The Vikings did not use coal, they used charcoal. This seemingly simple detail profoundly alters the chemistry of iron. Charcoal burns differently, releasing less sulfur and introducing specific amounts of carbon and phosphorus into the metal. These irregularly distributed elements contributed to forming a surface that was naturally more resistant to atmospheric oxidation. The fire itself contributed to the future protection of the object. Nothing was completely under control, and that's precisely why the result was resilient. In modern workshops, the goal is to accelerate production. Giant blast furnaces operate continuously, churning out tons of steel per hour. Industrial scale demands speed, predictability, and cost reduction. In the Viking world, time was part of engineering. Each batch of iron required days of preparation. The collection of the ore depended on the seasons. The charcoal had to be produced slowly in earthen kilns. The forging process took place in repeated cycles of heating and cooling. Metal was slowly learning how to exist. Today, a metal object is often designed for future replacement from the start. Modern economic logic accepts obsolescence as inevitable. Screws, hinges, tools, and structures are designed within predictable cycles of wear and tear. But for a society living in hostile territories, where resources were limited and winter could disrupt any attempt at restocking, durability was no luxury. It was about survival. A single nail that fails could compromise a vessel. A corroded chain could destroy a port. A broken tool could mean hunger. Longevity was not a cultural preference. It was an existential need. And perhaps it is precisely this environmental pressure that shaped Viking technical intelligence. They were not seeking to master iron with scientific precision. They were seeking to create something that would age well within an unpredictable world. Nature does not produce uniform perfection. It produces adaptation. Forests endure because they are diverse. Ecosystems survive because they are not identical. The human body itself withstands damage thanks to biological redundancy. Viking iron followed this same natural logic. While modern engineering often attempts to impose absolute order on matter, the blacksmiths of the North worked in cooperation with uncertainty. They accepted variations, responded to the behavior of the metal, and adjusted the process in real time. They didn't just manufacture objects. They were engaging in dialogue with the material. And the more researchers study these ancient artifacts, the more an uncomfortable conclusion emerges. Part of human technological knowledge has not been surpassed. It has been abandoned. The Industrial Revolution brought efficiency, scale, and abundance. But in doing so, it replaced slow, sensory processes with automated systems that rarely allow direct interaction between craftsman and material. The hammer was replaced by the machine, the human ear through the electronic sensor. The time frame depends on the production schedule. And perhaps, silently, something essential has been lost in this process. Because when we observe a piece of Viking iron still holding up after almost 1,000 years, we are not just looking at an ancient metal. We are looking at a manufacturing philosophy based on patience, observation, and a deep understanding of natural limitations. An engineering that didn't just ask questions, how to produce, but how to stay. Viking iron was not just strong. He aged differently. This detail begins to completely alter how we understand the relationship between ancient technology and modernity. Because resistance does not mean the absence of wear and tear. Nothing escapes time. Not stone, not wood, not metal. The real secret lies in as something is deteriorating. When archaeologists unearth Viking weapons, tools, or metal structures from the ground, they rarely find objects that are intact in the modern sense of the word. There are marks of time. There is oxidation. There is transformation. But what's impressive isn't the absence of rust. It's the controlled way in which it occurred. The metal doesn't collapse. It doesn't fall apart into fragile layers. It does not lose its structural integrity quickly. He matures. Metallographic research has revealed that many Viking artifacts developed a kind of protective patina over the centuries, a stable surface layer that drastically slows down new chemical reactions. Instead of continuously corroding, the iron reaches an equilibrium with the environment. Rust ceases to be a destructive force. It becomes adaptation. This behavior resembles natural phenomena observed in rocks exposed to the sea or in ancient trees that survive hundreds of winters. The surface changes first, absorbing the impact of the environment to protect the interior. The Vikings seem to be learning how to survive. And this characteristic arose not only from the material, but also from the way the objects were used within Nordic culture. Nothing was disposable. Tools were repaired repeatedly. Blades were reforged. Nails were reused generation after generation. Iron lived multiple lives within the same community. Each cycle of heating and hammering reorganized the internal structure of the metal once again. Small cracks were closed. Accumulated stresses were redistributed. The piece evolved along with its use. Today, we call this maintenance. For the Vikings, it was continuity. The very modern idea of replacing damaged objects would have been incomprehensible in many Scandinavian villages. The energy cost of producing iron was enormous. Cutting wood for charcoal, feeding the furnace, working the metal for hours. It all required collective effort. Iron carried human value. And when something has profound value, the way it is constructed changes. Blacksmiths did not work merely as isolated artisans. They occupied almost symbolic positions within society. They were mediators between fundamental elements: earth, fire, air, and water. The act of forging possessed a practical dimension, but also a cultural and spiritual one. Metal was not inert matter. It was a visible transformation. This mindset influenced technical decisions without requiring formal scientific knowledge. A blacksmith learned to recognize when the iron was tired, when it needed to rest after successive thermal cycles. He learned to respect the invisible limits of matter. Modern industrial production rarely allows for this type of direct observation. Machines don't perceive fatigue in the same way that human hands do. Sensors measure temperature. Algorithms control pressure. But no automated system senses the material's behavior at the exact moment it changes. And perhaps this is where one of the most profound differences between ancient iron and contemporary steel emerges. Modern steel is designed for immediate performance, high initial resistance, high structural precision, high manufacturing efficiency. Viking iron seemed designed for progressive longevity. He didn't need to be perfect on the first day. I needed to survive the 1,000th winter. In the Scandinavian fjords, where salty air constantly assaulted any metallic surface, objects remained exposed to extreme freeze-thaw cycles. Water seeped into microfissures, froze, expanded, and exerted internal pressure, one of the most destructive processes for any material. Nevertheless, many structures endured. The reason may lie in the microscopic flexibility of wrought iron. Unlike certain extremely rigid modern steels, Viking iron possessed the capacity for deformation without immediate rupture. It absorbed environmental stresses instead of directly combating them. It wasn't the hardest material. He was the most tolerant. In nature, the strongest organisms survive less often than those capable of continuous adaptation. Trees that bend in the wind survive storms that topple rigid trunks. Viking iron followed the same evolutionary logic, and this realization is beginning to challenge a deeply modern belief: the idea that technological progress is always linear. Because when studying these artifacts, an uncomfortable possibility arises. Perhaps some ancient societies were not technologically inferior. They were simply driven by different priorities. While modernity seeks speed and scale, the Viking world sought a balance between matter, environment, and time. They weren't producing any faster. They produced goods to outlast themselves, and as excavations continue to reveal objects that have survived for centuries under harsh conditions, it becomes difficult to ignore the silent question that accompanies each discovery. How much knowledge has been lost, not because of failure? But is it due to the excessive success of modernity itself? Perhaps we haven't forgotten. Asto makes strong iron. Perhaps we've forgotten. Because do it this way. There is a curious moment in the history of human technology when progress begins, quietly, to replace understanding. The Industrial Revolution not only accelerated metal production, but it also changed the very relationship between humans and the materials they shaped. Iron ceased to be something rare, acquired slowly through collective effort, and became abundant. Abundance transforms priorities. When iron was scarce, each object needed to justify its existence for decades, sometimes centuries. When the metal began to be produced in tons daily, the logic changed. It became cheaper to replace than to preserve. And at that historic moment, something essential began to disappear. Viking blacksmiths worked on a human scale. Each piece carried unique variations. Each batch of ore had its own behavior. The necessary knowledge could not be completely standardized. It depended on continuous observation, adaptation, and accumulated practical memory. Modern industry solved this problem by eliminating variability. Blast furnaces began operating at temperatures capable of completely melting iron, allowing for the removal of almost all natural impurities. The result was modern steel, more uniform, more predictable, and ideal for mass production. A technological triumph, but also a philosophical rupture. By purifying the metal, the industry removed not only defects, but also certain emergent characteristics that arose from the internal complexity of ancient iron. Natural inclusions disappeared. Heterogeneous structures were replaced by highly organized crystalline matrices. The material became perfect, and at the same time more dependent on external protection. Anti-corrosive inks, galvanizing, chemical coatings, constant maintenance. Modern steel rarely protects itself. It needs additional systems to survive in that environment. Viking iron, on the other hand, carried its own built-in defense from birth. Its resistance wasn't added later. It was part of its structural identity. This contrast reveals something deeper than a simple technical difference. It reveals two distinct ways of thinking about engineering. One attempts to predict and control all variables. The other accepts the natural complexity and works within it. In Norse settlements, survival depended on observing the environment. Houses were built partially buried to retain heat. Ships were flexible enough to absorb violent waves. Tools were designed to function even when imperfect. The logic was never to eliminate nature. He went to cooperate with her. Modernity often views nature as an obstacle to be overcome. Steel must withstand the weather. Concrete must defy time. Structures must remain unchanged. But the physical world is not static. Temperatures change. Humidity varies. Pressures build up slowly. Extremely rigid materials can fail precisely because they resist the inevitable changes in the environment too much. Viking iron survived because it was willing to change. This idea is beginning to resonate beyond metallurgy. Contemporary architects are re-examining ancient buildings in search of passive solutions. Engineers are analyzing historical materials to understand how structures endured without modern technology. Scientists are investigating abandoned artisanal processes to discover emergent properties that are impossible to reproduce industrially. The past no longer seems primitive. It starts to seem experimental. Perhaps the Vikings weren't trying to create the strongest metal possible. Perhaps they were creating the metal most compatible with the real world. And this difference completely changes the meaning of innovation. Because innovation isn't just about doing something new. Sometimes it's about relearning what worked before. In the silent fjords, where remnants of ancient ports still emerge from the cold water, iron chains continue to support weight after almost 1,000 years. Not by miracle, not by chance, but that's because they were conceived within a mindset where time was considered an integral part of the project. Each object carried an implicit expectation. It should outlive its creators. Today, many products are created with the opposite in mind. Designed for short cycles, designed for replacement, embedded in economic systems that value constant renewal. Rust then ceases to be merely a chemical phenomenon. It becomes a cultural symbol. It reveals not only how the metal was made, but how the society that produced it understood the future. And perhaps that's why the study of Viking iron holds such persistent fascination. We're not just analyzing ancient technology. We are facing an uncomfortable question. Progress has made us more capable, or just faster. Viking iron didn't survive by chance. It endured because it was born from a different relationship between humankind and time. It wasn't created solely to function in the present, but to transcend generations. Each hammer blow carried a silent intention: permanence. Today, we possess more powerful machines, more advanced laboratories, and incomparably greater scientific knowledge. Yet, many of the objects we produce are born with an invisible expiration date. Perhaps the true lessons left by the blacksmiths of the North are not limited to metallurgy, but in terms of mentality. They didn't just ask how to build something. They asked how long should that continue to exist. And that question changes everything. Because, in the end, the durability of any creation, be it metal, a house, or a civilization, depends less on immediate strength and more on the wisdom applied in its creation. If this type of content has sparked your curiosity about ancient knowledge, forgotten engineering, and the secrets that the past still holds, subscribe to the channel to continue exploring stories that time has almost erased.